So let's get started. So welcome back, everyone. So thanks for coming on Thanksgiving week. I know, so some people are traveling. So it's only Tuesday. So it's still not that early into the week. So great. We are so we're finally here. We're finally at the classification section. Classification is kind of the part of data analysis that is kind of basically the core thing associated with like machine learning. So if you wanted to learn about machine learning, we're finally at the end of the semester, finally kind of getting into kind of the heart of machine learning. So I hope that this section of the class, now that we've built everything up and we've gotten here, this should be fairly straightforward. They'll say, okay, that was pretty easy. So maybe we could have, it would have been nice to kind of learn about this earlier, but I think it will be easy because we will have seen almost everything here before. It's gonna it's gonna build on a lot of ideas from regression, but it's gonna be different. We're gonna need to think like linear algebraically in ways that we use in like dimensionality reduction. We're going to need to use gradient descent and stuff. So there's going to be kind of, if we had started with this, would have been so many new ideas at once. At this point, there are going to be a few key, new ideas that really help simplify things. And so in today's lecture, we're basically going to start with linear classification. Define the problem. We're going to get you to kind of how to solve this, how this is typically solved through gradient descent. And we're going to go by talking about these loss functions. These loss functions is kind of where the action is when thinking about linear classification here. Right. So, okay. So that'll be today's lecture. A little bit, why did it do that? Okay. A little bit look at the schedule. We are getting near the end of the semester. We're starting the last section of the classification. The next few lectures, starting next week, we're going to talk about the perceptron algorithm. The perceptron algorithm is kind of one of the oldest algorithms in some machine learning and data analysis. It was probably from the 50s, if not so earlier. This is kind of a simple way of doing gradient of doing linear classification, or kind of it can be generalized to these kernel cases and SVMs of doing classification that does not require all the machinery of gradient descent. You can say a lot about it without going through gradient descent. So it's a little bit more concrete to really understand the basics of what is going on. Then we're going to generalize this to kernels and SVMs. So next week, these are going to be kind of a more powerful way of doing linear classification. And then finally, the last lecture, we'll get into things like neural nets and decision trees, and kind of give you a taste of like the potpourri that is machine learning. I'll say a little bit about here why, kind of give some insight into why things like neural nets and random forests, which are based on decision trees. These are kind of the two methodologies which have been making lots of kind of breakthroughs in machine learning. And we'll get a taste of them here, and then I'll explain how these kind of give some insight into why these are kind of moving beyond what has been done with linear classifiers, which kind of, that line of work kind of continued up through these kernel methods. Right, and then the neural nets will also build on the perceptron algorithm is used inside of neural nets, right? So it's not kind of just something from linear classification. You can see it inside of the neural net algorithm if you know where to look. And so we'll see how these kind of are kind of building on everything else, and give some perspective of where this is going at the end. And then we'll do a review in the last day of class. Kind of important thing, the homework 5 is out. Let's look quickly at homework 5. It's not due until what I say, December 10th, right? I'm not, finish it when it's convenient for you. It's not like you're going to be, if you do it by December 10th, we should hopefully be able to grade it before the final, which is our goal. That's why it has that deadline. If you finish it early, you should be able to do actually most of it after today's lecture. You should be able to do most of it already. Okay. Right. So the first question is on clustering, and I just want you to make sure you understand the mechanics of it. So basically, how this assignment function is working with some small example, and then we'll look at the mixture of Gaussians where you actually define a small Gaussian and again have to compute like these soft assignment weights. If you can do this, then you can figure out how to probably iterate this in these other algorithms up to the kind of all these other messy details. Question 2 is also about clustering, kind of about where it can get stuck. And then question 3 will be about loss functions and linear classification. Question 4 will be about perceptron algorithm as well as the kernel ideas, right? So that one, you might not have all that for a few more days, but you can definitely get started on this. Okay, so if you have a chance, yeah.
So on that homework, I saw you use the word univariate.
Yes.
What is that?
Means one variable. Let's see, where is it?
It's up on the matrix. Right by the covariance matrix.
Oh, yeah. So univariate is not. Oh, yeah. Univariate is not the right word here. Well, maybe it's the right word. Okay, so what that's saying is that the covariance matrix we're talking about, it's going to be a diagonal matrix, and the covariance values are going to be the same everywhere on the diagonal. It's also two-dimensional. So there's only one variable which is describing it. So that's why what the univariate is supposed to be saying. It turns out you don't need to use the covariance matrix form to write this. If you remember from when we talked about this in the lecture, you can actually just divide the squared distance by sigma squared, or sigma in this case, and it should work. It should work as well, right? So you don't necessarily need to go through the covariance matrix if you kind of make sure you don't square sigma j here, right? But we try to give you so the point is we didn't want to make this too complicated, so we just gave you kind of a one variable which is describing it. Yeah, but another way you can think about this is it's a uniform stretching in all directions, but univariate here refers to one variable, and yeah, so it's one variable is describing the covariance matrix here. Yeah, great. So okay, good. So good question. All right. So let's get on with the lecture. All right. So classification. All right. So classification is kind of the core problem. Classification is kind of the core of machine learning, okay? And it's going to be taking as an input X and Y, right? So this is going to be a supervised problem where we're going to try and learn a function on the X variables and predict the Y variables, right? So like regression here, right? And so the X we're going to say is going to be a subset of RD. We can think of X equals to X1, X2, up to Xn. These are all points in RD. And the Y now is not going to be real values. These are going to be, usually the Y is going to be, so the simple case, just so two classes. It's like a binary variable, but it will be more convenient to think of it like -1 and +1. Okay, so if you had 0, 1, that would be fine. There's a class I can map it to -1, +1. I can multiply times 2 and subtract 1. If it's a binary variable, then I get -1, +1, right? But it's a binary variable describing two classes. Okay, so the idea is that X is kind of is the attributes of some data, and Y is the is the outcome, right? So in regression we had similar, but the outcome was like a value. This is discrete. I don't care like what, you know, so like if I'm a company and the X corresponds the data of a customer, and I'm looking at, am I making a profit? How much profit do I make off of that customer? Well, I'm caring about, do I make a profit or do I not make a profit, right? If anyone is profitable, well, then I want them as a customer, right? I care less about how profitable they are. I'll take as many profitable customers as possible, I guess. If I'm playing a sports game, right? Say a sports game, it's kind of like I don't know the lingo. Like, okay, so if there's a game you're playing, you're trying to predict a game for so for the purposes of betting, or if it's in the win-loss column, that's all that matters. Do you win or do you lose? Okay, so if you're doing like fantasy football, where you're getting points, then you're doing regression. If you're kind of betting on the outcome of the game, or you're worried about the win-loss column, then you care about just the outcome, just the win or the loss, right? So if you're doing some health studies and you're doing a treatment, ultimately the most important thing is, does someone live or does someone die, right? These are the kind of some binary outcome. Okay. There are sometimes different grades of these things, but we're focusing on this binary outcome. There are these two classes, right? So this corresponds with two classes in the outcome. There are ways to extend all this to multiple classes. They're typically fairly straightforward, and but we're not going to get into them in this course. If you understand how to do binary classes, there's often kind of a few simple things you can do with multiple classes. Either kind of learn a classifier for each individual thing versus everything else, or you can somehow phrase it as a single big optimization. There are a variety of ways. The two class case is the most interesting case here. Okay. Okay. So I'd like to, and again. Okay, so the goal is so function from F to from RD to -1, so +1. So such that, and there are two ways of so thinking about it. One is on so data xi, so yi, which is in xy. I want f of x I to be equal to yi, right? So I want the function to predict a -1 or +1. I want that to match the value I get on the data. In general, what you actually want is to assume that each xi, so yi, is drawn iid from some unknown sort of distribution, right? So this guy is an unknown distribution, okay? And I want to build F such that on so new data X, Y, that's also from this same distribution, that F of X equals Y, right? That I tend to get this. Now, I'm not necessarily going to get this on all the data, but I want in general for this to be true, right? I want maybe on as many data points as possible this to be true, that they exactly match, right? So kind of being close, you know, it doesn't count, so it doesn't necessarily cut it anymore, right? If I'm, well, I thought it was +1, but I predicted -1. Are those close or are they not close? It's really a binary thing. I want them to match exactly. I want to see how many can I get to match, right? So on the data I have, I want to basically count, so I want this on as many as so possible. All right, and okay, so I can try and learn on the data I have, right, on the training data, but what I wanted to do is work good on new data I don't have yet, right? So I can do a cross-validation here. This is supervised. It's a supervised problem, which means I have cross-validation. So typically, you would take all the data you have and you split it into two parts, the training and the test, right? And you do as well as you can on the training data, and then you kind of evaluate how well you did on the test data. And the test data should look like data from the same unknown distribution, but you haven't observed it yet. If you didn't use it in the training, you might as well not have observed it yet, so that you can kind of see how well you're actually doing, right? The goal is to make a function which is making good predictions on new data, right? All right, and so again, I'll emphasize this point because the last two sections, dimensionality reduction and clustering, we were not doing supervised learning, we're doing unsupervised. And there it was more about the shape of the data, and we kind of were trying to kind of come up with a simple shape or model of what was going on. Here again, we're coming up with a simple model, but this is a predictive model here, and we can actually measure the prediction in the way we've talked about before. Okay. Okay, so this function, you know, if I can build any function, well, then I can just, you know, I can just output -1 or 1 on the data I have, but I want this to be kind of simpler functions tend to generalize better. And yeah, so again, so Occam's razor, so this is basically one way of writing this is simple models tend to generalize so better. All right, so we're going to want to come up, we don't want just any function, we're going to want a function which is going to be so simpler. This is kind of, this flies a little bit in the face of models from like, so deep learning and like decision trees, where these are very complicated models that tend to generalize better than these so simple models. I'll try and give a sense of why this is still a good way to think about it when we talk about these like neural nets and stuff. This is still generally true, but they're kind of the class of problems where you would want to apply linear regression and these sort of methods, and deep learning are not necessarily going to be the same. So okay, so we'll kind of so we'll come back to that. But in this context, where we're going to start is basically the simplest function we could think of to make this prediction? Well, the simplest function would just be a constant function, but we're going to be strict for the, at least for the next couple of lectures, that f is a linear function. Okay, and so a linear function of f of x, remember x is going to be, I'm going to call this x1, x2 up to xd. Yeah, we'll typically use the subscript to describe the to describe which data point it is. So I'll use the superscript here to describe which coordinate it is. Again, this is a d-dimensional vector. Okay, so that means we'll use a model which is going to look like x1 plus x2 up to plus xd, and we're going to have some coefficients in front here, alpha 1, alpha 2, didn't need all the space there, alpha d, and we'll have an alpha 0 in front here. Okay, so this is what the linear model is going to be. It's going to be, I'm just adding up all the components and I'm scaling them, and there's a linear coefficient in front, and there's an offset coefficient in front, right? So the linear model, we've seen this before, is going to look just like this. In fact, it's common to actually not write it with alphas in this case, but to actually, it'll be much more useful. Whereas in the case with regression, we'd want to kind of combine this into a single dot product where all the alphas were folded in. We're going to want to not do that and keep the offset term separate and call this W1, W2 up to WD. So now B is going to be a scalar value and W is going to be RD. And so we'll typically think of our model described by these two terms, this W vector and this offset value, scalar value B. Okay, so this will be the parameters of the model. All right, so for next thing we'll kind of explain what this function looks like using these parameters. And in the lecture on Tuesday, we're actually going to assume that B is 0 instead of and I'll give an intuition why you can do that. But the perceptron algorithm does not know how to handle the value B, so we'll have to kind of deal with that in a special way. But we'll see. It's not a big deal. Okay. So this is our linear function. We've learned about linear functions before. This should not be kind of new or surprising. But what's wrong here? What are we missing? So again, we wanted to predict something where f of xi equaled yi. Well, yi was either -1 or +1. Actually, so I'm going to change this. I'm going to say learn a function f where g of xi is equal to yi, and g of x is equal to y, and g of x is going to be the sine of f of x. So it means it's going to be +1 if f of x greater or equal to 0, and -1 if f of x is less than 0. Don't worry so much about what I do if it's equal to 0. You choose one of the two, right? But g of x will convert it to the sine. What I really care about is kind of the sine of this function, right? So it's a linear function, but I'm kind of I'm kind of capping it. I'm kind of snapping it to -1 or +1 at the value of the sign. Okay, so if it's greater than 1, if it's greater than 0, I say it gives me a prediction of +1. If it's less than 0, it gives me a prediction of a -1. So there's this kind of really big transition at 0 here. Okay, but because I have a class, 2 classes, and that's my goal, well then, this is what I need to do. I'm not predicting a scalar value, I'm actually predicting a one of these 2 classes, a -1 or +1. So I'll start with the scalar value and then I'll round it to -1 or +1. Okay, and this will lead to some difficulties we'll see, right? So I have a linear function f, but then I'm gonna kind of take the sign of this linear function. Okay. All right, so let's say and so I'm going to add that. So typically we're going to restrict that W is equal, the norm of W is equal to 1. So that means it's just direction. Okay, it's not capturing, again, the scale information. It's just capturing a normal. We'll see a normal direction, and B will capture kind of this offset. We'll see what this means. Okay, so we are given a G of X equals sine of F of X, and F of X equals B plus the dot product of W and X, right? So this is a compact way of writing it. And we'll assume W is equal to 1. If W is not equal, if the norm of W is not equal to 1, you can kind of factor that difference into B, right? You can always, if you basically divide B by the norm of divide B by the norm of W, then you kind of, you would recover this solution, right? So if, yes, okay. So what is the interpretation of what is going on here? Okay, so we're gonna have some data points, and I'll usually, what's common is you kind of draw them as like the data point as, these are some data points that are the ones labeled -1, and there are other data points labeled so +1 here. Okay, and so these are the data points. These are kind of X, Y, where Y is either minus or plus, right? And now we're going to be given a, and so in order to understand kind of what the geometry of this linear classifier is doing, we're going to need the notion of the origin, right? These have coordinates, so these are in our RD, and this is the 0. Okay, and so the linear classifier, if we do this correctly, is going to be represented by a line, and so in this line is going to divide the space. Now, if we're in RD, we're in higher dimensions than 2. It's not just a line, but it's actually a half space. I'm cutting the space in half. And the normal direction is, so W. W will be pointing towards the points which are so positive, right? The normal direction is pointing in the direction of the positive points, right? The positive points tend to have more negative values than the negative points, the +1s. So W is kind of facing its coordinates are negative, right? So then the dot product is going to be large, if I have a smaller value of the coordinates for the positive points. Okay, and then B is going to be this length here. B is this offset. Okay, so W is the normal direction of this half space, right? So now it's a half, if it's a half space, that means it's D minus 1 dimensional, right? So this is D minus 1, so dimensional. So it's not good, think of it as a line, think of it as a cutting the region into two halves, right? And it's the D minus 1 dimensional plane describing it. And I can describe that by a normal direction. That gives me the direction that's normal to the plane, right? So it can be a sheet of paper in R3, and then the normal direction tells me I can categorize the kind of this plane by the normal direction, but then how far it is off the origin is what B tells me. So if I have a normal direction that's off of the origin, if W was instead, you can kind of imagine kind of a W that's here. If this was the normal direction, well, that would say if the sign was negative, right, this would correspond with a different half space, so that only this one plus point has the dot product with this, only the one plus point in the bottom left. If the dot product of its coordinates with W is greater than 0, is positive, then that's classified as positive. But I want all of these plus points to be categorized as positive, so I need to subtract a value here. So in fact, this is going to be, so B is going to have a negative value in this case. Okay, so I'm actually in the direction of W, I'm adding B. In this case, it's a subtraction, right? This is actually, so negative B, right? So it's the length in the direction of W, and it's negative, so I'm subtracting off the effect of B in this case. Okay, so oh no. So I'm, that's not right here. I'm thinking, if I think through the math here, it's adding B to it, right? So this, let's look at this point here. If I call this X, Xi, the dot product of W and Xi is going to be, let's say this value, it's going to be this value here. Let's say this value is 3, but B is equal to, say, 7, right? So that distance is 3, but it's in the opposite direction. So it's actually, it's minus 3. This dot product is minus 3. So minus 3 plus 7 is equal to 4, which is greater than 0. Okay, so all of the plus points except for that one have actually a negative value if I take the dot product, but if I add a value of B to it, well, then I'm bringing those back above 0. But if I look at a different point up here, maybe W dot, this, call this guy Xj, W dot Xj, this might be minus 10, and so minus 10 plus 7 is still equal to minus 3, so the sign here is negative still, okay? It's kind of the geometry of what's going on, right? And so this is kind of a fairly simple, right, so this is how this linear model works, and I want to, and this gives me the dividing line, that green line, that thick green line here, is kind of really is dividing the region where that function is going to predict negative, right? Over here, it's predicting that it's negative in the shaded region, and everywhere else is positive. So it gets this kind of, this is what a linear function gives me, a linear, so decision boundary here. This is a linear decision boundary. Okay. Great. So this is how a linear, the shape of what the linear classifier is doing. It's finding points in a high dimensional space, finding a linear decision boundary, and you're trying to separate the positive points in your training data from the negative points in your training data with this function. And it's about the simplest function we can come up with that's going to do that. All right. Okay, so is the problem now, okay, so now we say the input is xy, x is in, let's just say this is in RD cross -1 + 1, and then the intermediate goal on the training data, let's say this is the training data, the intermediate goal is going to be find linear f, and this is parameterized by W and B, from RD to -1 and this is from RD to R. So the sign of f of xi is equal to the value of yi here. Okay. All right. So this is our goal, right? And what we're going to talk about. So today and also the lecture on Tuesday. How do we solve for W and B? All right, so how to solve for W and B. These are what describe this model, right? So f has to have the form, right? F of x is going to be B plus the dot product of W and X, right? So how are we supposed to solve for this W and B? All right, there are at least two things from the course so far that we can apply, and they're both going to be a good start towards doing this. And so we're going to discuss both of those. We kind of know how to solve this. If you ignore, right, there are a couple parts that are a little bit problematic with how we've done this before, so we're going to need to correct them, but I want to kind of bring it back to techniques we've used before in order to solve for quite similar problems. All right, it's been a long semester. I will help you guys out a little bit. The first one is apply our linear regression algorithm. Okay, the linear regression is solving a very similar problem, and I should say kind of least squares. Okay, the least squares linear regression problem. This is similar. The least squares linear regression problem, it solves for WB to so minimize, right, the sum over I of kind of f of xi minus yi squared, right? So we're trying to, this is looking at, this difference as the residual and squaring it and trying to minimize the sum of those. And we know how to do that. We know the output of it is a linear function, which is what we want. And this seems fairly close to what we want. If the function predicted, right, if we met this exactly, this might give us a great solution, right? The yi's are either -1 or +1. So if we got really small error, then the f function would actually give us -1 if yi was negative and +1 if yi was positive. If we could do that, then that would be great, right? So this linear regression function is not so bad of an idea. In fact, it's not unheard of to solve classification problems this way. Okay, sometimes this would be called like the least squares, or the kind of the squared error, so loss function. Here, we'll talk about loss functions a little bit later in this lecture. And so this is not unheard of to actually use. So it's kind of, it's okay. But I want to just show an example of why this is not always exactly the right thing to do. Although not so always. Okay. Let's look at example. I can just draw it fairly simple here. This will represent RD. So this is where all the X points are going to lie. And we'll say that the Y values are an R, and we know that they're either going to be at -1 or they're going to be at +1. Okay, so now I can draw, let's get my color coding correct. Let's draw that the positive points are going to be up here, and the negative points are going to have these minus values. Right, they're all exactly on -1. All the positive points have a Y value of exactly +1. Right, we can think of this as Y in here and X in here. Okay, and if we were to do this perfectly, there's kind of, this lives in RD, right? So this one line is trying to capture all of RD, and there's some half space that goes through here that can divide these perfectly. Right? I could potentially find this great half space that goes through here, but what a linear regression model will do is it will find a linear function. We'll find a linear regression function that might look like this, right? That's trying to minimize the sum of the squared errors. Right, minimize the sum of these residuals. And right, because you have a bunch of negative points pulling it down, you might get a function that looks like this. And the resulting classifier you're going to get is where it hits 0. And you might get these two positive points misclassified. Right, there was a better function here, right? This purple choice, right? This purple function, this is the optimal, but this might be from least squares, so linear regression, right? So we're finding a linear function. Right, so this green one is a nice linear function. So this fits our model that we wanted, and then we rounded it at -1 +1. But the cost function we optimized, the sum of the squared errors, did not know that we were going to be rounding it at 0. We're going to be giving it, so it said that the cost function of these two positive points misclassified. Well, it said, yeah, that cost was maybe slightly more or slightly less than 1. I don't really care so much. That doesn't change so much. I'm more interested in keeping the cost of the extreme points, extreme positive and negative points, from being misclassified. I really don't want those to be misclassified. So I'm going to not worry whether this cost function kind of right here, if these values are going to be kind of positive or negative, I predict they're very close to zero either way. So it doesn't take that into account. Okay, so it still does a reasonable job here. It's not so bad. And if I had, the first time I tried to draw it, right, it maybe actually got the right answer for those points. Okay, so, but if you work this out, you can generate a solution where, the linear regression will give you the wrong answer for this model for a number of points here. When there was a better solution, not very far away, that it could have been used, right? So it could have instead used a function, kind of ideally, it would have used a function that looked like this. Right, if I use here, and this is the decision boundary, it's going to get everything right. But this has worse error, right? It's not going through the blue negative point. So the linear regression error for this one, how I've drawn it, is worse. Okay. Okay, so linear regression, we can solve it, and this is kind of everything we know about this. This one had a nice closed form solution, but we could use gradient descent, right? So what if we tried to directly optimize, right? What I would like to do, okay, so I'd like to use gradient descent. So can we use gradient descent to minimize? Okay, I'm going to try and write down what the cost function we want to minimize is, and I'm going to call this delta of g of alpha of x, y. And so this will be I equals 1 to n of 1 minus, write this. This is an identity function. Let me write up the rest and then I'll define that. The sine of yi is equal to the sine of f alpha of xi, when this could be maybe simpler, just y of I is equal to g of alpha xi, right? Where g of x is equal to where g of alpha is equal to the sine of f of alpha. Okay, so this is what I'd like to do. This term here, this guy is known as the identity function. If you haven't seen this before, this takes in so binary values, say true, false, and it maps to 0, 1, right? Where if it's going to be equal to 1 if true and 0 if false. Okay, so if these match, right? So if these guys, if these values match, if the prediction matches the right class, the right sign, yi is equal to g of alpha, g alpha of xi, right? Then I get a value of 1, but I want to minimize this, so I do 1 minus that. Okay, so typically the identity function gives you, I could also do, and get rid of the 1 minus and have a not equals. Maybe that's more intuitive, but this is kind of the common way of phrasing it. And I want to count those. So this is giving me the count, right? So I'm summing over all of these. This is equal to the number of misclassified points. Okay, so I just want to minimize the number of misclassified points. Okay, And so now, can we use gradient descent to minimize this cost function? Okay, so this is what we'd like to do. We'd like to find the classifier which minimizes the number of misclassified points, right? If I do it, if I misclassify all the, or don't misclassify any of points, right? Like the purple one here, that's the optimal. The green one is not minimizing that function, it's minimizing something else and is making some error. If there happen to be a lot of points in between here, the classifier might be doing a much worse job than it could be, because I was minimizing the wrong thing. So this is what I'd like to minimize, the number of misclassified points. Okay, can I use gradient descent with this function? Right, we talked about taking the least squares function from gradient descent, and there's a lot of machinery. It actually simplified really nicely. We all implemented this for your homework, right? And we could use gradient descent to minimize this. It's decomposable, right? That part is nice, right? Because it's a sum over a bunch of individual terms. It's decomposable. I could potentially use stochastic gradient descent. Is this something we can do? No, it's not. Okay, I see some head shaking. Great. The answer is no, right, for this question. No, we can't use gradient descent. And there are two main reasons why we can't do it. One, it's not so convex. As we'll see, actually, in a couple weeks, that convexity is not the be-all, end-all of when you can use gradient descent. But even worse, there's no so gradient. Okay, I can't define a gradient for this. It is basically a piecewise constant function. Okay, so g of or delta g alpha of x y, if I write this as a function of alpha, it is piecewise constant, and then it has jumps. Okay, so if I try to draw this weird picture, right, where this is kind of alpha 0, alpha 1. I think we tried to draw this for linear regression. We got these half pipes, if you kind of remember that picture. Well, in here, we're going to get this really weird situation, and I don't know exactly what it looks like. But you're going to have these regions where it's going to be constant in this region. It's going to be constant in this region. You know, how many ever misclassified points we have, right? Each of these regions has a constant number of misclassified points. So if I move alpha parameters a little bit, I'm not going to change the result of how well I'm doing. So, even if there's a minimum, maybe the pink region is the region with the minimum cost, right? But how do I know what direction to go if I'm sitting in the green region, right? So I can't, this function is like not compatible with gradient descent. So I can't really use that one either. Okay. All right. So we've done a lot of stuff where we borrowed from earlier in the class, and now we're going to add a little twist to this, and then we're going to get everything to work again. Okay. So okay. Good. So how do we solve this? We're going to use these ideas called loss functions. Okay, and the basic idea of a loss function is to basically approximate this delta function. Okay, so that delta function, right, this is what we wanted to minimize, the delta function, and we're going to approximate that. Okay, so let me kind of rewrite up in order to do that, it's going to be useful to kind of change yeah, so to kind of change rewrite these expressions, right? The bottom here, I have this delta function, which is delta g of alpha of xy, but I really want it as a function of alpha, right? So let's just rewrite this in a way that'll be a lot more convenient here. So we're going to think of a function f of alpha, and this will be the function which we are going to kind of plug into gradient descent so eventually, okay? And this is going to be some loss function, which I'll define, of g of alpha of xy. So it's going to approximate this big delta, right? And remember, this is decomposable. This is still going to be decomposable. And I'm going to have a lowercase l loss function here of g of alpha of xi, so yi. Okay? Right, so I'm going to have this g function, which is going to give me a sign based on xi, or something like a sign based on xi and yi. And this is not here. It's going to be, yeah, comma here. Let me put a comma of, so it's not g of alpha of xi and y, g of alpha comma xi and y, right? So I'm not going to apply it on xy. I'm going to take the function and apply it on the set. Same way the loss function is going to take in, L is going to take in the g of alpha function that makes the prediction, as well as a data point. And it's going to output some score. Okay? But the first kind of trick I want to do is I want to write this. And so this L, why I wrote L above, is this one here, this is going to be a bivariate. Okay, so we're going to get into bivariate and univariate functions. Again, this will be a bivariate version. So I'm going to combine these two versions, these two objects together. Be more convenient to write this out directly in this clever form. L, and this could be a version of this which is going to be univariate, L of alpha. I'm going to write this as Zi, where, so this is now univariate. Okay, so it's abusing notation a little bit here, but we're going to do this as Z of I is going to be equal to Y of I, G of alpha, Xi. Okay, this trick is actually so pretty cool. So let's look at this guy here. What's going on here? Y of I, G of alpha, Xi. This is going to be greater than 0 if yi is going to be less than 0 and g of alpha of xi is less than 0, right? So if the true value was negative, right, if y of I was negative and g of alpha of xi was also negative, well, then they match. That's great. It's going to give me a value which is greater than 0. It's going to be greater than 0 if y of I is greater than 0. So let's say it's a positive value, and g of alpha of xi is also greater than 0, right? So if it's positive and I predict positive, I also get a value greater than 0, right? But I get less than 0 if so let's say so otherwise, which is a bad prediction. Okay, so if this is saying I'm going to get a positive value if these things match, if yi and g of alpha xi match in terms of sign, and a negative value if they don't match, right? So this will be a kind of a very convenient form, okay? And then, but what I'd really want to do, remember I wanted to write this in terms of alpha here, right? So let's change this one more time to write I'm going to write this as f of I of alpha, right? Because this is a decomposable function. This allows me to say f is decomposable, right? Because then I'll be able to apply stochastic gradient descent, which is nice. For this, I'm going to have f of I of alpha is just going to be equal to the loss function of z of I equals y of I g of alpha xi. Okay, so kind of once I have the loss function and I can do this conversion by doing y of I times my linear function, right? Then I'm going to get this function defined for each of the data points. And it's going to be decomposable, so you get the full loss function. I'm just adding all these up. Okay, now it's a function of alpha, and I can think of running gradient descent on this. Okay, so what this is going to mean is that, let's say the L is good if it's convex. Okay, so there's first thing is convex. 2, if it has a so if it has a gradient, right? To run gradient descent, I need to be able to calculate the gradient. Let's see it. And then 3, if it's going to approximate, so delta. And I'll explain what I mean by this a bit more on the next slide. Yeah.
So that equation in the red box, are we checking quality? And if so, how does that?
Yeah, so I'm just defining. It's think of it more as the definition. It's L. I'm just defining some I'm defining a loss function, which I haven't told you what L of alpha is yet. I guess this should be L of alpha. So L of alpha will be a function which I'm going to give you some examples. That there's not one choice anymore. There's going to be several modeling choices you can do for L alpha. But it's going to have, the total optimization is going to have this form, and I'm going to have to choose L alpha, and I'm writing it this way, so I'm pointing out that f is decomposable as a function of alpha. And so then I can run my stochastic gradient descent.
So if I understand correctly, we're actually just backing in the I, L, and equal sign there. Fine.
Yeah, so the green and the red boxes are just defining what these are here. Yeah, right. So the kind of the actual equation that you want to look at is here, and the green and the red boxes are defining what's happening in those steps. So I'm just reading. I didn't change. I'm just giving you the definitions. I'm just giving you definitions here of how this fits together. And I haven't explained what L alpha is going to be yet, okay? But it's going to be a bivariate function that takes in this green equation, which combines together our linear function and our data. Okay, so we're going to have a linear function. We're going to have that this guy is going to be is linear. We'll actually be able to plug in a kernel function in for here later as well, so we can make this nonlinear. but in general, this will be linear, combine the data, and it is univariate. So it'll be easier to think about. And so now we want to look at these loss functions, L alpha, that satisfies these properties. It's going to be convex. It has a gradient, so I can run gradient descent on it. And if I, add together a bunch of convex things, they're probably going to be strongly convex if I do it correctly. And I want them to somehow approximate delta. Okay, so this is kind of the big picture. This, if I can do something like this, I can throw it in gradient descent. And this is how most of machine learning works. Yeah.
So quick recap, L takes in ZI.
Right, it takes in ZI, which is just a single value. And if it's positive, it's good. If it's negative, it's bad. Yeah. Great, so maybe we'll come back to this. Let me try and define delta in these terms and the loss functions and give some examples, and then we'll kind of see what is meant by all this. All right, so again, we're going to have ZI, which is going to be yi some g of alpha of xi. G of alpha is the function we're learning, and basically if ZI is kind of good if greater than 0, or otherwise is bad, right? Okay, and so let's kind of quantify this. In fact, right, so this will be kind of this will be R, but this will be the ZI value. Okay, so let's think of the ZI value here, and this is going to be 0. And what this delta function is going to look like here, right? This delta function that we're going to want to kind of approximate so this is going to be our delta loss function. Okay, so I'm going to have this will kind of be like this value, where this is the value 1 and this is 0, right? So if I get so think of I want a small value. And this is this delta function I want to approximate. And if my ZI value is greater than 0, right? Right, it's good. This is ZI greater than 0 is down here. This whole region on the right of the 0 is good, and left of 0 is bad. Right of 0 means I've classified correctly on this data point. Left of 0 means I've classified incorrectly, right? So classified so correctly, and this is classified incorrectly. Okay, and there's this big jump here, right? And this function is not convex. You can see why it's piecewise constant, right? I can change, I'm changing the prediction of a data point by changing alpha, right? This alpha value changes the prediction, and that ends up where when I pass it through this delta function, it changes the score. But if I change alpha a little bit, it'll change ZI a little bit. And it's not going to change the value. It's going to stay constant. And then there's a big jump, right? So I can't really take a gradient of this function. But this is the cost function I actually am working with here. Okay, so let's see some examples. Again, so delta is going to be equal to 0 if kind of delta of z if z is equal to or is greater or equal to 0, and 1 if z is less than 0, right? So this is the function that I'm starting with, and I'd like to approximate this function, but with something convex and it has a gradient. Okay? Okay, so let's start with the most common, so loss functions. Okay, there are a bunch of choices here. Okay, and the most common one is called the hinge loss, or at least the simplest first one we're going to talk about. And that's going to be L of z is going to be equal to the max of 0 and 1 minus z. Okay, so what does this look like? Okay, well, I'm going to take up, I need to identify this point at 1 here. And the hinge loss is going to be 0 if I'm greater than 1. And it's going to come up like this. All right, so this is going to be the hinge loss function. Okay, so this is convex function. I draw kind of the midpoint in between any 2 points on the curve, and it's above the curve, right? It's convex. It's mostly differentiable. It's not differentiable at 1. If zi is equal to 1, then it's not differentiable, but it's almost everywhere differentiable. And in fact, the derivative is really easy, right? It's a linear gradient here, and it's got a gradient of 0 here. So what is the same? If I classify really well correctly, really far, I'm very far away from the decision boundary. My zi value is going to be large. If it's greater than 1, then I don't actually, it has 0 penalty. That's great. It's approximating 0, so it's good. If it's close to the decision boundary, right, the zi value is positive but small, then I start to have a penalty. And that penalty increases as a linear rate, and it keeps getting worse as I cross over the decision boundary to misclassify. Right? So I can think of having kind of my decision boundary, and right, so this is the positive points want to be on this side, and I can think about kind of 3 choices here. Let's say this one might be zi is equal to +2. This might be zi is equal to plus 0.5. And this one is zi is equal to -1. Right? So as I'm on the right side, the further away from the decision boundary, I get a big zi score and I get 0 penalty. If the zi is close to the decision boundary, if I'm close to the decision boundary, like this point here, well, then there's some sort of penalty, right? And then the penalty keeps getting worse and worse. I cross over. So I can't have a big jump here. That's impossible with a differentiable and convex function, but it's pretty close. So this is kind of the closest convex function in some ways that approximates and upper bounds this delta function. Okay. Intuitively makes sense. So I can then, this can be my cost, and if I optimize this, it works pretty well. I have to have a special treat. What happens if I'm exactly here? Well, maybe I pretend that the derivative is 0 at that point. Okay, so I need to have a case statement. So but it's doable. You can run gradient descent with this, but it won't be strongly convex. Yeah.
Wouldn't outliers break?
Well, so if you have a really poorly misclassified point, right? So if I have, right, so if I have a point that's way off here, right? It's way on the wrong side, right? So this one says, yeah, I've got an example that this decision boundary is really bad. maybe I should like rotate it and try and pick off that point. In high dimensions, you actually have a lot of flexibility in how you can rotate around data. Now, if I have other negative points that are pushing it back, well, I'm going to absorb that. Maybe I can't classify correctly all the points. The optimal may not classify all the points correctly. That might not be possible. And we'll see a little bit about going to nonlinear classifiers that allow me to kind of predict larger models next week, Thursday, right? But I might not be able to classify all of them. It'll find, if I optimize this with gradient descent, it'll be convex. It'll find the global optimum out of all functions, which minimize the sum of all these costs. Because it's convex, I can get the optimal solution, right? So it will, however I choose to penalize it. This one is actually not so bad with outliers. Okay, let's look at the next one here. The next function is often called the smoothed hinge. Actually, let me actually start with the squared hinge, and then we'll compare this with the hinge loss. The squared hinge loss function, this is going to be equal to the max of 0 and 1 minus z squared. Actually, squares on the outside. Okay, let's look at the smooth hinge loss function. Okay, what is this going to look like? It's going to be, well, it's going to be the same here. This is the smooth up until if the zi value is greater than 1, that's going to give me a value of 0. And then it's going to look like this. This is going to be the smooth hinge. Okay, this one's going to be even worse with outliers. Okay, this one, if a point is misclassified, once I get past, I get error, it's really going to shoot the cost up. It's going to go up at a rate which is quadratic with the distance. Relative to that, the hinge loss function is more stable with respect to outliers. In fact, it's really the kind of thing of the difference between the mean and the median. The hinge loss is kind of like finding the median, which is robust to single outliers, where the squared hinge loss is like finding the mean, which can indeed be pulled by individual outliers. Given this cost function, again, it's going to be convex. In fact, the gradient is defined down here, which is great. So its gradient is defined everywhere, and it's smooth, right? It's still piecewise defined, so I have to have a case statement, but the gradient's defined everywhere, and this one you can get to be, will often be strongly convex. As long as you have a unique minimum, it will be strongly convex, and then you will find it very efficiently. If I have enough data, right? And there's not a perfect classifier, yeah. Okay, so this is a squared hinge loss, but this so we mentioned this one is worse for outliers. So another version of this is often called the smoothed hinge. And this is defined, L of z, it's going to have 3 case statements now. It's going to be 0 if zi is greater or equal to 1. It's going to give 1 minus z squared over 2 if z is if 0 is less than or equal to z is less than or equal to 1. So if z is between 0 and 1, it's going to look like the squared hinge, but with the 1/2. And then it's going to be 1/2 minus z if z is less than 1 or is less than 0. Okay, so what is this one going to look like? This one's kind of the best of both worlds. It's going to be the same here, a 0 cost right of 1. It's going to look like It's going to go up at half the rate, right? So it's going to be quadratic in this zone, and then it's going to be linear. So this is the smoothed hinge loss function. And so this is going to be differentiable everywhere. I have 3 case statements. It's not going to be an upper bound on the delta function, but it probably doesn't matter so much. And it doesn't kind of really have a squared penalty for outliers. So this one is actually pretty nice. Okay, let me show one. Okay, we've run out of time. Let me show one more, and this is the last thing we really need to cover. This is called the logistic loss, and if I optimize this, is called logistic regression, and this is L of z is equal to natural log of 1 plus x of negative z. Okay, it's kind of a weird natural log 1 plus e to the negative z. It's kind of a strange function, but has no case statements. And if I draw it, it looks, it's going to look kind of like this. Okay, it's kind of okay. So the way to think about this, maybe the way to think about this is to first draw what's called the ReLU. Okay, so this function is so the ReLU is kind of the hinge that's been shifted to have the hinge point at 0. This is called the ReLU, which comes up as an activation function in deep learning. And then the logistic loss kind of approximates the ReLU. So this is the logistic loss. It asymptotes with this kind of the same as the hinge. So it basically grows linearly as I get further out, and it asymptotes at 0 on the other side. But it's like there's no kind of case statements you have to define. It's differentiable, and its gradient is bounded in a nice way. It doesn't approximate, doesn't upper bound the delta function. It upper bounds the ReLU. If I wanted to, I can shift it by 1. I could do a 1 minus z or minus z plus 1 in there, and then it will approximate the delta or the hinge function. But this is typically what's called the logistic loss. And so this is also another nice one. Again, these are going to give me things which are going to be kind of convex, if not strongly convex. I plug them into a gradient descent, and I can solve this basically optimally. Okay, so that's end of today. Went a bit over. We'll talk about another algorithm from first principles, the perceptron algorithm, next week, Tuesday. And you can get started on your homework. Have a great Thanksgiving break. Yeah, rectified stands for rectified linear unit. Yep. So that's just some nomenclature. We will mention it again in the